I want you to imagine the most terrifying hiking trip of your life. You are dropped onto a random mountain range in the dead of night. It is pitch black. You are blindfolded. You have no map. You have no GPS. You can't see the peak above you, and you definitely can't see the valley below you. Your goal? To find an absolute lowest point in this entire infinite landscape, the bottom of the deepest valley, before you freeze to death. How do you survive? You can't teleport to the bottom. You can't see the destination. You have only one tool: your feet. You feel the ground immediately around your shoes. You tap your right foot. Does the ground slope up or does it slope down? If it feels like it's going down, you take a step. Then you stop. You feel the ground again and you take another step. This game of survival is gradient descent. It is the engine of all modern artificial intelligence. In our previous video, we built the car or the neural network, and we built the map or the loss function. But gradient descent is the driver. It is the algorithm that actually navigates the complex multidimensional mountains of data to learn the solution. Today, we are going to master the math behind the hiker. We'll cover derivatives, the learning rate, the danger of saddle points, and the critical difference between batch, stochastic, and mini-batch descent. By the end of this video, you will understand exactly how ChatGPT finds its way home. Hey everyone, welcome back to Sumantra Codes. I'm Sumantra. If you are just joining us, we are in the middle of deep dive into fundamentals of deep learning. Let's recap where we are. We have a neural network with parameters or weights and biases. Let's call them theta. In modern network like GPT-4, there are 1.7 trillion of these parameters. That means our mountain range has 1.7 trillion dimensions. Second, we have a loss function j theta, like mean squared error, that gives us a score. High loss means we are standing on top of a mountain. The model is dumb. Low loss? We are at the bottom of the valley. The model is smart. Our mission is simple. Move theta around, tweak those 1.7 trillion knobs until j theta is as small as possible. Mathematically, we want to find theta star such that argmin of all theta j theta. In a simple world with one weight, the landscape look like a bowl. Let's say we initialize our weight randomly at w equal to 5. We are here. The loss is high. We want to get to w equal to 0, where the loss is minimum. The question is, which way do we move and how far? If we move right or increase w to 6, we go up the hill. Loss increases. Bad. If we move left or decrease w to 4, we go down the hill. Loss decreases. Good. This intuition, go downhill, is the essence of gradient descent. But how do we calculate downhill mathematically when we can't see the curve? To know which way is down, we need calculus, specifically derivatives. The derivative of a function tells you the slope of the tangent line at a specific point. It tells you the instantaneous rate of change. Let's look at this point. The slope is steep and positive, which means dj.dw is greater than 0. Let's say the slope is plus 3. This means if I increase w by a tiny bit, the loss j will go up by 3 units. Now think about our hiker. We want the loss to go down. So if the slope says going up is positive, we must go negative. We do the opposite. What if we started here? The slope is negative, pointing down to the right. dj by dw is less than 0. This means if we increase w, the loss goes down. So we should increase w. We should go positive. Do you see the pattern? Gradient is positive, go negative. Gradient is negative, go positive. This leads us to the golden rule of gradient descent. Always move in the opposite direction of the gradient. So the formula is w new is equal to w old minus gradient. Quick terminology check. In one dimension of one weight, we call it a derivative, which is dj by dw. In multiple dimensions or with many weights, we collect all the derivatives into a vector and call it a gradient, denoted by nabla j or del j. It's the same concept. The gradient is just a vector of arrows pointing up the steepest hill. We turn 180 degrees and run to the other way. So we know which way to go. Now we need to decide how big of a step to take. If the slope is really steep, should we take a giant leap or a small shuffle? In machine learning, this step size is controlled by a hyperparameter called the learning rate. We denote it by Greek letter alpha or eta. Let's update our formula to the final version. W new is equal to W old minus alpha into dj by dw. This number alpha is arguably the most important setting in your entire neural network. Why? Let's look at the Goldilocks problem. If alpha is tiny, like 0.000001, you take a microscopic steps. Yes, you will eventually reach the bottom, but it will take you 10 million steps. The model trains forever. Your GPU credits will run out. Your startup goes bankrupt before the model converges. Verdict: safe but too slow. If alpha is huge, like 1, you take a massive jump. You see the valley, you sprint and you overshoot it completely. The slope here is even steeper. So your next step is even bigger. You jump back to the right, but even higher up. This is called divergence. Instead of converging to 0, your loss explodes to infinity or NaN, and the verdict is catastrophic failure. If alpha is just right, maybe 0.01 or maybe 0.001, you take a healthy step towards the valley. Crucially, look at the math again. W nu is equal to W old minus alpha dot slope. As you get closer to the bottom or the minimum, the slope naturally gets flatter or closer to 0. Since we are multiplying by the slope, our steps automatically get smaller as we approach the destination. We settle in gently, like a golf ball slowing down right at the hole. Verdict is convergence. Now, I've been lying to you slightly. I've been drawing these nice, perfect U-shaped ball. In math, a bowl shape is called convex. If your problem is convex like linear regression, gradient descent is guaranteed to work. It's like rolling a ball in a smooth bathtub. There is only one bottom, you cannot fail. But neural networks are non-convex. The landscape of a deep neural network doesn't look like a bathtub. It looks like Himalayas. It has peaks, ridges, multiple valleys and holes. Look at this small dip here on the left. If our hiker starts near it, they will roll down into it and stop. The slope is 0 at the bottom. The algorithm thinks, I'm done, I found the bottom. But look over there to the right. There is a much deeper valley, the global minimum. The hiker is stuck in a local minimum. They found a good solution, but not the best solution. This is even more common in high dimensions, or like 10,000 dimensions. A saddle point is a point where the landscape curves up in one direction, but down in other direction. Right in the middle, it's flat. The gradient is 0. If the hiker lands here, they stop. They have 0 gradient. They think they are at the bottom, but they are actually standing on ridge with the cliff on both sides. Escaping saddle point is one of the biggest challenges in training deep networks. There is one last critical variable, data. To calculate the true slope of a mountain, we need to calculate the loss for every single data point in our dataset. If you have 1 million images, you have to run 1 million images, calculate the average loss, and then take one step. In batch gradient descent, or as the perfectionist, you look at all data points before taking one step. The pro of this is that you take a perfect step downhill. The con of this is that it takes hours to compute just one step. It's like measuring every inch of ground before moving your foot. You'll never get there. Second, stochastic gradient descent, or the drunk hiker. You pick one random image, you calculate the loss for just that image, you take a step. The pro is it's blazing fast. The con is the gradient is noisy. One image might say go left and the next might say go right. Your path looks like a drunk walk. You wobble around but generally head downhill. Then the third one is mini-batch gradient descent, which is the sweet spot. This is what we actually use. We grab a batch, say of 32 or 64 images, we average their loss, we take a step. It's stable enough to be accurate, it's fast enough to train on GPU. When you see batch underscore size equal to 32 in your PyTorch code, this is what it means. You are telling the hiker, check your compass every 32 step. So, how do we fix getting stuck in local minima and saddle points? We give the hiker a heavy backpack. We give them momentum. Imagine a heavy bowling ball rolling down the hill. When it hits small local minimum or a pothole, does it stop? No, it has inertia. It rolls right through the small dip and continues to the big valley. This is why we rarely use vanilla gradient descent in production. We use smarter algorithms like SGD with momentum, which adds velocity, or ADAM, short for adaptive moment estimation, which is the gold standard. It adapts the learning rate for every single parameter individually. We'll cover ADAM in a future video, but just know standard gradient descent is the theory, momentum or ADAM is the practice. Let's recap our journey to the mountain. First, the mission. We want to minimize loss J theta. Second, the derivative. The gradient points uphill. We subtract it to go downhill. Third, the learning rate, the most important hyperparameter. Too small, which means slow. Too big means it will diverge. Fourth is batch size. We usually use mini batches, 32 or 64, to balance speed and accuracy. Fifth, the trap. Beware of saddle points. Use momentum to roll through them. Next time, if you train a model and see a loss number ticking down on your screen, 0.5, 0.4, 0.3, visualize the blindfolded hiker. Visualize them taking millions of tiny steps, terrified of falling off a cliff, trying to find the bottom of the valley. That is the struggle of intelligence. I want to know, have you ever had a model that exploded? Loss went nan? What was your learning rate? Let me know in your debugging war stories in the comments. If this video helped you to visualize the math, smash the like button. It updates the gradient of the YouTube algorithm in my favor. Don't forget to subscribe to Sumantra Codes. Keep optimizing and I'll see you at the global minimum.